that's where I did my PhD. And I'm currently a professor in volcanology here. And hopefully I will work again in Kawajan very soon. I'm still working a lot with some colleagues in Indonesia. Okay, so well, you might know all these things and have seen probably that a few times already. I'll just check the time. Feel free to interrupt me at any time, at any slide, if you have any question. It's much easier than going back to slide 20 when it's finished. You know that context, I guess. Still, I think it's quite important to start with this. Kawajan is, well, the Ijen caldera is located on the eastern part of Java Island, quite close to Bali, as you can see. So it's the yellow arrow with Raung here. It's a big caldera, and of course it's due to the subduction that occurs from the Australian plate towards the north, and that gives rise to all these volcanic edifices that you can see here. But you probably know that. And within the caldera itself, of course, you have Kawajan, which is the most famous, but you have quite many volcanoes that are not currently active. You have some volcanoes located on the border of the southern border of the caldera in yellow, and then you have all the intra-caldera volcanoes in blue. And then you have the rim of the caldera, the northern rim, close to Blawan waterfall to the north. And there are many, many interesting things to investigate within the caldera itself. Of course, the most famous is the acidic lake, but there's also the Banyu Pait, Banyu Putih after, that has been studied by many, many volcanologists, including Vincent van Isberg, and including someone who is just sitting next to me in the office next to me, Alain Bernard, who did one of the first work in Kawajan more than 30 years ago now. So Banyu Pait is really an iconic river and is very important for geoscientists in general. And I'm going to show you the formation of the caldera itself. So the caldera, it's a bit more than 20 kilometers of diameter. That's more or less, so it's a bit more than that, I think. And there were 4 stages that were that developed and produced all the things that you can see here in different colors. So first, the caldera formation that occurred around 30,000 years ago, so quite a long time ago. And well, you probably know how caldera forms, but basically it's a big explosion, big eruption. All the magma is drained, and when the magma is out, you just have something which is pretty flat and which is empty by the eruption itself, and that forms a caldera, which is kind of circular or elliptical in this case. So that was more or less 30,000 years ago. And then there were domes that formed to the north, on the northern rim, Gunung Ringgi, that you can see here in green, for example. And then some edifices that formed on the border of the caldera, the Gunung Suket, Jampit, Rante, which are quite massive volcanoes. So it's quite, as you can see here with the digital elevation model, it's quite big edifices. And then finally, there was effusive, so mostly lava, gentle lava emission at the surface, effusive volcanism within the caldera itself. It's the blue edifices that you can see here. And there were many of them, and they most likely were formed thanks to a fault that is roughly aligned on the east-west direction. And then, of course, there is the active volcanoes, Gunung Raung on the west and Kawajan on the east, which are shown here with this nice pink color. So part of the job we did, well, it's more than 10 years ago, I did that with Antoine Triantafilou, who is now a professor in France, and who basically mapped all the directions, all the faults that you can see in Kawajan. We did that by going to the field during numerous field work, but also using satellite imagery, because thanks to the satellites, you can study the volcanoes from space. You can also monitor them, but I'm not going to talk about that today. But you can, for example, follow the deformation of the volcanoes from space. And in this case, he mapped all the different structures that you can see within the caldera to know how, what are the main directions, if you will, of these for this caldera system and for within the caldera itself. And that's all the lines that you can see here. And you see that overall we have different directions, but there is a main direction which is east-west, and that could explain all the small volcano that you have in the center of the caldera. Oh, in total, we have more or less 3 faults. This is a geological map that I think we collected in Bogor, thanks to a cooperation with the CVGHM. And that shows you the main units that have been mapped over the last decades within the caldera itself. And there are 3 main faults which are quite important here. It's the Pedati, Blawan, and Jampit faults that you can see one of them here. Again, it's more northwest, southeast, more or less. But these are the main structures that are found within the caldera, and that you can again find in the satellite imagery. Okay, now the geological context. It's more, I would say, the context of Kawajan. As I told you, I mostly focused on Kawajan myself. The last magmatic eruption was a bit more than 2 centuries ago. That was quite a big eruption. It occurred in 1817. And there was a lot of ash. Some roofs collapsed. There were some victims. So it was a big eruption. But since then, so more than 2 centuries now, the volcano has mostly experienced phreatic eruptions. And phreatic eruptions are eruptions that are not involving any magma at the surface. So it's purely steam and gas, sometimes a bit of ash, but you mostly have non-magmatic emission at the surface. And of course, Kawajan is really well known for the acidic lake, which is more or less always around a pH of 0, 1 sometimes even below 0, which is very acidic. So sometimes we say that it's hyper acidic. And it's been like that for, again, 2 centuries, more or less, with temperature most of the time between 30 and 50 degrees centigrade. So that's a photo we took a while ago now. And the volume of the lake itself is 30 million cubic meters. So it's a huge lake, huge acidic lake, the world's largest currently. And when I arrived in Kawajan in 2009, at that time there was 1 seismic station installed on the summit in Puncak, and that was not recording at that time, but there was some maintenance. And my PhD thesis was mostly focused on seismic recordings, trying to improve the monitoring network, but also to find new proxies to monitor the volcano itself. So that's a photo that most likely you know, sulfur miners. But before going into my work, well, it's part of my work, but what we did together with Vincent van Insberg and many colleagues is to better understand a volcano, you usually need to study his history and know what he has been doing for the last decades, centuries. So what we did is that we collected as much information as possible from the library of CVGHM in Bandung, where there's a lot of very useful information. I took this book because I found it back today. It's the history of Kawajan that you can find in the Bandung library. We also found information in the Tropen Museum, which is a museum. They have a collection, and the museum is located in Amsterdam, in the Netherlands. And there's a lot of very interesting photos and books, and also old books, like the one you see on figure 5 here of the review paper we wrote about Kawajan. And all this information allowed us, together mostly with Vincent van Insberg, to reconstruct the timeline of the activity, of what we can know about the magmatic eruption a bit more than 2 centuries ago, what was known before that, and what happened after that. And for example, I show you here a sketch in figure 4 on the right side of the screen. And you see the situation of the crater with the lake, but at that time you see the fumarole were not, most of them were not within the lake waters. There was, of course, some active fumaroles as today, not submerged with water, but there were more fumaroles that were not covered by water. And we compared that with the extension of the crater now today. And so that's very interesting because you can then compare how the volcano has evolved, at least over the last 200 years. I'm showing you here a photo from a report that we found in Bandung, and you see that at that time the Dutch, I think, installed a house on top of the Puncak. Well, it was really literally on top of the summit. So there was an observatory located on the volcano itself, on the Puncak, and you have the bunker that you can most likely most of you know. So you see the bunker that's still there today. The observatory is not there anymore. And they were monitoring the lake, but also meteorological parameters, and which is very useful for us, because as you can see here on the right side of the slide, every day they were collecting the level of the lake. They were collecting information about the rainfall, how much rain was falling on a given day. That's what you see at the bottom of the graph, and the lake water temperature. And that was in 1941, so that's a while ago. And what you can see here, for example, just by very quickly looking at the dashed line on top of the graph, the level of the lake, you see that there is a sudden decrease in the level of the lake. For example, in this case, it's in April. And what they did is that they opened this, they call it a sluicing event. So they tried to remove the excess of water that there was in the lake to prevent any lahar, because there were often lahar. So the lake was much bigger at the time. It was 40 million cubic meters, so 10 million cubic meters more than today. And to prevent any lahar, they were just opening the drainage here so that the water could flow. And you see that when the level was decreasing, the temperature of the lake was increasing, which makes sense, because if you have a constant input of heat towards the system, if you decrease the level and the volume of the lake, you will heat the lake. And this is the kind of information that are very useful for us to understand how the lake is behaving and is evolving through time. So that's a photo of a sluicing event at that time. That's another photo. You see that the lake was very high, much higher than today. We have all the people that were taken here with the photo. And that's the kind of thing I was trying to explain. That's an early interpretation of the volcanic lake activity more than a century ago. It's by Artman, a Dutch, not a Dutch, a German. And he shows his understanding of the volcanic lake, the crater lake. And, yep. Is there a question? No?
I think no.
No.
You can continue, Corentin.
Okay. Well, again, feel free to interrupt me at any time. If there any question, just feel free to ask it. But yeah, what I'm trying to show you here that I reproduced from this very old book, that when you decrease the gas pressure, yeah, go for it.
No, you can continue. Maybe the question will at the end of your presentation.
All good to me.
Yes.
So if you decrease the pressure on the lake, they realized that there were more bubbles coming at the surface, which is of course very concerning for the people who are working around, for the tourists. And one thing, or one way to explain that, is that if you think about a boiling pot of water, the amount of water that you have in this pot will of course influence the boiling that you can generate. And that's exactly the same idea here that he tried to reproduce, that if you decrease the pressure on the system, you will have more bubbles at the surface. And this is something very important because it helped us to understand why there were more bubbles in general during the rainy season, for example, at Kawajan. So all this historical information has been very, very useful for us scientists, and but also for the people in charge of the monitoring. So Paeri and Parjan, when I was working there, were discussing that with us, and that was very useful. And I'm going to show you one more photo of how people were collecting measurements in 1916 and what we were doing in 2010, so 2010. And you see that they were actually much better equipped than we were, with bigger boats than my small boats here. That was a bit dangerous. I think it's not a good idea to sail on the lake. I wouldn't do that anymore. And we had some scary moments, but that was very useful to collect information, of course. And in the end, one of the last thing we did in terms of collecting historical information was to compile all the reports that have been produced by CVJHM since 1990. So it's every week, sorry, people, the observers are climbing on the volcano, taking temperature measurements, level measurements. They are also observing the color of the lake. That's the green, white, and gray colors that you can see here. And you have also, of course, since 1987, I think, you have the seismic activity that is also analyzed. You have many earthquakes, and I'm going to get back to that a bit later. But this is very useful to understand all the unrest that Kawajan has experienced over the years, and to better understand and to better monitor the volcano in the future. So I'm not going to detail the plots here, but that's the kind of information that we have tried to collect with our colleagues from Indonesia. And that's an example of a phreatic explosion in 1993. There was a tourist, who took this photo, and you see that's quite impressive. In that case, it's better not to be close to the lake shores if you see that kind of event, because it's very massive. It's quite a large increase of lake level. And of course, it's hot and acidic water. There's also gas. So it's very useful to have that kind of document, but you better not be there when that kind of small phreatic explosion occur. Okay, so back to my work. As I told you earlier, when I arrived on the volcano in 2009, 2010, there was one short period sensor that was installed in the Puncak, on top of the volcano, on top of the crater, on the southern rim of Kawajan volcano. And we tried to install different broadband instruments, and I'm going to explain you what a broadband seismic station means. We installed 3 of them, one close to the main path when you are going towards the rim, to the crater. It's called station PSG, and 2 on the crater itself. And we also installed another site close to the dam. And to complement or better understand the volcano and the velocity model, because that's going to be very important for us to better understand and locate the seismic earthquakes, we also installed during a few months 5 short period sensors, plus 4 that were moved around in the caldera. So in total, we had a really good network at that time, together with our colleagues from Indonesia, from CVJHM, the observers, and some colleagues who are currently based in Bandung. We had in total 12 stations at some point installed on the volcano, which is very important because it helps you to better locate the earthquakes. On top of that, my PhD thesis was trying to better understand the lake system. And to do that, I installed a few temperature divers. So the divers are just instruments that you put in the lake. I'm going to show you a few pictures. And a leveling station, but also a meteorological station. So that's, of course, to build a seismic station, you need to bring a lot of water. So for one seismic station, for a very good instrument like a broadband, it takes about a week to construct a good seismic vault. And so that shows you a map of all the instruments that we managed to install over the years. You have some stations in green that have been installed by USGS, so our colleagues from the US, the VDAP group, who did an amazing job to install some stations on the volcano itself, but there was also one in the Pos and 2 close to Raung. And then the blue ones are the short period stations that we installed in the caldera itself. You have the one in red, which are also short period stations, and some broadband sensor that were installed. That's one of them is PSG in pink, one is the dam, one is Pos Baru, and there was also one in Puncak, the one I described earlier, which is co-located with the station from CVJHM. Okay, so that's for the seismic station. When it comes to the lake, as I said, the main objective was to better understand the lake itself and how it works, because until 2010, most of the efforts to understand the lake were focused on the geochemistry. So people in the 80s and the 90s were very attracted, of course, by the lake, which is super special, very acidic, as I said, super hot. And so the colleague who's sitting 3 offices next to me was there. It's Alain Bernard, and he collected water samples. He studied the lake in detail, but from a geochemical point of view, analyzing the ions, the anions, and the cations. And my job was to better try to understand the geophysics of the lake. So I installed a few temperature sensors within the lake, close to the fumarole, close to the Solfatara, but also in springs from very close to the crater in the Banu Pait. So close to the gypsum waterfall, for example, here. Maybe you know Pahim. It's him on the photo here. And just to show you an example, it's of course very challenging to install instruments within the lake for the reasons I described, the acidity, of course, but also the very high temperature. And hopefully the video work, but if you put the sensor, and this is iron, it's not iron, but it's metal, you have a high corrosion. So we have to find very specific protection within the lake. So we used sort of PVC bottle that I can show you here. So I don't know if it's clear. It looks like this, and we install the instrument inside the bottle. We put a lot of water so that it's well coupled to the lake temperature, and then we leave it in the lake for a few months. Unfortunately, we lost a lot of instruments because of the nasty acidity. But in the end, we managed to collect temperature data every day. And we had one value every hour for many years. So it allowed us to better understand how the volcano was behaving. And as I said, so we put some sensor in the lake itself, but also in the Banu Pahit river in 3 different spots. So we basically climbed to the dam and then went down along the Banu Pahit, but also started from the main road to install one sensor close to the road. And these are all the sensors that we installed over the years. Again, to get a value every hour. So that's one of the sites. We installed one station, one temperature sensor in a cave, which was of course ideal because it was well protected from the rainwater. And based on a model developed by Vincent Hinsberg and his collaborators, this spring is supposed to reflect what is going deep in the system, so directly in the deepest part of the system, of the hydrothermal system, and not from the lake, which is very useful because it allows us to better understand how the volcano is behaving, what is coming from below, what is going on the surface. And it really helped us to better understand the structure of the system itself. As I said, we also try to install leveling sensors. So that's one of the level sensor that I installed in 2010. And I was very happy. I put it in the water in June, and yeah, in June. No, that was in June. So I installed it during the rainy season when the lake level was very high. It was in the lake, and when I came back in the dry season, it was not in the water anymore. And I protected it with Teflon because Teflon can resist to acid water. So that was very useful, but unfortunately, a water level sensor which is not in the water anymore is not very useful. So that was we learned a lot of things in terms of protection and all these things, but we lost a lot of sensors. And finally, to better understand how the lake is behaving, it's important to understand what the environment is doing and how much rain falls in the crater. So to do that, we installed a pluviometer. So it's a rain gauge that you can see here, which collects water from the rain, and also wind data. Because when you have more wind on the surface of Kawajan, you lose calories and the temperature decreases. So it doesn't mean that the volcano is less active. It just means that there is more wind. And so we have really to understand the environmental condition a bit better to better understand what is going from the magma intrusion towards the surface and better monitor the volcano. Unfortunately, this was also used as a toilet by some people, so it wasn't always very representative for the rain, but that's also part of what we learned. And just to show you, I'm not again going to enter all the details because that's a lot of scientific content, but essentially what happens in Kawajan is that you have the magma, which is more or less located beneath, well, a few kilometers or a few hundreds of meters beneath the surface. And then you have this volcano hydrothermal system, which is dominated by vapor, mostly liquid, of course, because you have a large lake, so you have a lot of liquid. And then you have rain and you have evaporation, which is why we installed a wind sensor and an anemometer and also a rain gauge. And this all together allows us to better estimate what's going in the lake itself and hopefully to better monitor the volcano over time. And as I said, you have the river, which is also important, of course. Okay, that's it for what we installed in the lake. I explained to you that we deployed a few things within the crater itself or close to the crater in terms of seismic instrument. So my main expertise is in seismology, and I'm going to try to keep it as simple as possible. What we study with seismometers, it's the ground vibrations. And to do that, we've studied waves. And what we will mostly try to characterize is the frequency of an earthquake, for example. In Kawajan, you have many earthquakes. Some of them are very high frequency, which means that you will have wiggles that are very close to each other over time. So if you have the time on the x-axis and the amplitude on the y-axis, there will be a lot of cycle. But you also have very long period activity and long period activity, which is very important as well, because it will help us to characterize Kawajan. And in that case, you have less cycles over time. So that's essentially what we wanted to investigate in the beginning of my PhD thesis. To do that, you have instruments. You have seismometers, and you have seismometers that are, for example, very short periods. And we call them short periods because they will be capable of deciphering or measuring all the ground vibration that are quite high frequencies. And this will be, for example, a normal car, a Kijang car. So not too expensive, but still very useful to do monitoring. Then you also have the broadband, and the broadband is much more expensive, but is very important in the context of monitoring Kawajan because it's sensitive to very long period earthquakes, which are quite common, especially when the volcano is more active. And those ones are sensitive to ground vibration with dominant frequencies or dominant periods, which are on the order of 40 or even 240 seconds. You need to imagine something which produce a wave that will last for 240 seconds and then start again. So it's an extremely long period event that you won't see with a short period sensor. But it's very useful because it allows us to track and understand the fluid movements. And as you know, there's a lot of fluid activity in Kawajan. So we installed both types of instruments. We were lucky enough to have 3 broadbands that we installed together with our colleagues from CVJHM, with the observers, but also with scientists like Padevi Shabana and others. And we installed that over the years, and it really helped us to better understand the volcano and hopefully improve the monitoring, thanks to a close collaboration with Papa Arjan and Paeri. So in the end, the seismic vault, the typical seismic vault we developed in Kawajan is this one. That's for a broadband. So the broadband is an amazing instrument. It's capable to record very long period waves. It's very sensitive, but the problem is it's sensitive to everything, to volcanic activity, but also to winds, to rain, to temperature variations. So it can be a bit tricky to understand what you are recording at the surface. To do that, you have the seismic pier where we put the sensor. That's here. The red sensor is the name Trillium. That was the name of the seismometer. And we have to pay attention to decouple that from the walls. You have the walls, then you have a gap, and then you have the seismic piers. Otherwise, if you have a lot of wind, this will be transmitted to the seismic platform, and we will record the meteorological condition, which is not what we want. So that's why we do that. And then we install styrofoam that we Paeri brought from, I think, Surabaya. And this is very useful because it allows us to protect or to minimize the influence from the temperature of the atmosphere and the humidity. So that was something very useful for us. And that takes approximately 1 week to construct. And then, of course, you have the digitizer, which is here, which is recording the data and which are stored on SD card. And you have the battery. So, of course, in this, you need energy to power a seismic station. And you have solar panels, which are very useful and which are critical to, again, deliver power to the seismometer. Okay, so that's it for a seismic station. In this case, it's the typical broadband station in Kawajan. And this is a few pictures to show you how it looks like on the field. So here we have the Puncak with the solar panel from CVGHM, Padang Geologi, and there was a seismic sensor installed within the bunker, and we installed another one at some point during a few months. That's the protection that we put just around the seismic station, and that's how it looks like when you are on the ground. You see the people who helped me to build the seismic station here. That's me trying to install the seismic station. That's a station on the dam, close to the dam. One of the sites we installed, one close to Pasbaru, and well, all the people that carried water towards the top of the volcano to construct the vault. Okay, so in the end, we have a seismogram, which is very useful because a seismogram can tell us something about the source. So the seismogram can tell us something about the source, but the problem is that you have all the information that the seismic waves will collect from the source to the seismic station. That's the propagation. And then you have also the information from the site of the seismic station itself. So if you install the seismic station on a lava flow versus something which is unconsolidated sediment, you will not have the same seismogram. So it's something we have to take into account. That's the site. So it shouldn't be the path, it should be the site here. Sorry, there is a mistake. And then you have also the instrument. And the instrument, of course, we have different instruments, so we have to take that into account. So the seismogram will be a combination of all these things. But when you have that, and imagine you have a few seismic stations, in the case of Kawajan, at some point we have 12 stations recording. You have an earthquake in red that will travel from the source region, from where it has been originated and triggered, up to the seismic station itself. And the cool thing is that it can tell us something about the region where it has been traveled to. And for example, in this case, it can tell you that this place is composed of harder rocks, and the seismic velocity will go faster. And the opposite is here. For example, if you have magma, the seismic waves will travel much slower, and you have seismic velocity which is much smaller. So it's very interesting because it allows us to understand how the volcano is structured and what is going on the volcano itself. For example, to know where are the magma regions. Just to show you a few examples of typical earthquakes. In Kawajan, you have sometimes volcanotectonic earthquakes. That's typically like this. So this is an example from Soputan from my colleagues from USGS. But most of the time in Kawajan, we have low frequency earthquakes. And those ones are very tricky to understand because they often occur on the volcano. And they can be due to fluid movement, to magma, contrary to volcanotectonic earthquake. A volcanotectonic earthquake occurs when you rupture the rock. So it's a brittle failure. Imagine that the magma is pushing towards the rock. At some point, it will rupture, and you will have this kind of earthquakes. Problem in Kawajan is that we have a bunch of other seismicity, low frequency. We have hybrid, and the name of hybrid is a good one because it's in between a brittle failure and fluid movement, in between volcanotectonic earthquake and low frequency earthquake. You have very low frequency earthquake, and then you have something which is really annoying, very useful, but very annoying, which is called tremor. And tremor is just something which has an amplitude above the background. In the case of Kawajan, there is often tremor, and it complicates everything because, for example, if a very tiny earthquake, a small earthquake, it can be buried or hidden in the tremor. But it can be also useful, as some of our studies have found or have shown with my colleagues from CVJHM. We found very cool things thanks to tremor in Kawajan. But typically, that's exactly what we wanted to investigate and what our colleagues or the observers of Kawajan are monitoring every day. Okay, I'm going to show you just one example of a very strange seismic event. In this case, in 2013, there were only 4 stations recording, because of course, Kawajan is difficult to maintain. There is a lot of acidity, so the solar panels are damaged over time. But still, our colleagues are doing an amazing job because there is a really good network and there is always data coming towards the observatory that are useful to monitor the volcano. So at that time, there were 4 stations. And you have the situation before the phreatic eruption into the March 2013. So you see that the lake is just normal, green, blue. And you have the situation just after the eruption. And you see that's quite different. So the lake is wide, there's a lot of gas. The temperature is actually close to 60 degrees centigrade, so you better not be there. And the volcano was, of course, evacuated at that time. And what we recorded with my colleagues from CVJHM is 2 things. I'm showing you here a seismogram of 1.5 hours. So in total, we have 1.5 hours. And you see what the short period sensor was seeing at that time. So you have lots of tremor here. You have a tremor burst that lasts for a few minutes. And you have some seismic events here, an earthquake here, and many bursts. And you see what the broadband seismic station sees. And the cool thing is that it allows us to collect new information and to better understand what the volcano was doing at that time and how it was behaving. And I'm going to ask you to focus on those small pulses that you see here. So there's one here that you can see hopefully with my mouse. There's another one here, and there's another one here. And this is called a very long period earthquake. Before that, so we had 3 years of data. We never saw any VLP, or maybe 1 or 2. And here, just within a matter of a few, 90 minutes, so 1.5 hours, we see 3 of them. We say, okay, there's something to investigate, and that will help us to better understand the volcano. And yeah, I forgot to mention that this is directly followed by another oscillation that lasts for tens of minutes, and that you can see here in blue. Now you can also see it in green and red. And for the seismologists that might be there, this is the motion, the ground vibration that you record on the horizontal component. You have the vertical component of the ground, and you have the horizontal components that are recorded. So if we zoom in on the first or one of the very long period earthquakes, that's what you can see here. It's like this, and then you have this long-lasting oscillation that lasts for 15 minutes. So this is very long. And if you analyze that with the broadband we had at that time located on the crater, we managed to know that the volcano was actually located here, to the northern eastern side of the lake. We also managed to estimate the depth of the VLP source, and you can see that it's just below the lake, so 700 meters below the lake, which is quite shallow. And what we think is that this is the very long period earthquake, and after what we see is just the resonance of the basin, so of the crater lake. So for example, imagine that you kick something, it can resonate. And we think that it's exactly what happened at that time. And the sulfur miners reported an increase of lake level. In science, we call it a seiche, and that's the name of this small increase of lake water, of lake level. And that can happen due to a phreatic eruption. So it's just a response of the lake itself to the volcanic long period earthquake. And this is, of course, very useful because now with Parjan and Paeri, we know that we have to pay attention to these very long period earthquakes. Okay, the last thing I want to cover in terms of seismology, I still have time to do that, is a new technique that has been developed by my colleagues in France. So until last year, I was working for IRD. It's an organism based in France, and I was working in Grenoble. And they used a really cool technique that we tested in Kawajan, which is not looking at earthquake. Most of the seismograms, when you take them, it's non-earthquakes. It's everything but earthquakes. We call it noise. If you use this noise, and I won't detail that because it's not important, if we do an operation between two pairs of stations, which we call cross correlation, you can get this kind of messy graph, which is called a cross correlation function. This is very useful. And why is it useful? Because it's like an image of the volcano between the pair station you're using. So imagine you have waves coming from the ocean, because there are waves that are triggered all the time, for example, in Bali Sea or in Java Sea, and that will propagate until the volcano and will sample the volcano. If you compute the cross correlation function between seismic station A and B, you can actually use the waves that have traveled all the time and that have spent a lot of time traveling in the volcano. So this is how a cross correlation function looks like. Imagine that you have another cross correlation function, let's say in 2 days, you can compare that to the cross correlation function 2 days ago. If the medium is changing, you can have something which looks like this here. You have a black seismogram cross correlation function and a red cross correlation function. And you see that there is some delay. They are not just on top of each other. This means that the medium has changed, that there's something occurring on the volcano. It can be due to rain. During the rainy season, the medium is changing. It can be due to magma. If the magma is pushing upwards, it can rupture the crust. So you'll have volcanotectonic earthquake, but the medium is changing. And that's exactly what we wanted to see. Back more than 10 years ago now, some scientists developed this technique and applied it to La Réunion Island, which is an island belonging to France, located close to, well, it's in Africa. And they compared the cross correlation function between one day and the other. And I'm going to ask you to focus on panel B. And you see that prior to the eruption, these are the green rectangle that you can see here. There are 5 eruptions over more or less 2 years. You see that there's a change before the eruption. That's something which has been highlighted with a red color. And this is a seismic velocity decrease. What does that mean? That your waves coming from the ocean are traveling towards the volcano. They are traveling within the volcano, but they are traveling much slower than before. So this can mean that, for example, you have a magmatic intrusion. If you have magma intrusion, you will open rocks. If you open earthquake, if you open rocks, or you will have seismic velocity that will travel much slower. And quite interestingly, that occurred without any earthquake. So in terms of monitoring, this is very useful because it can tell you something before seismic events, before seismic earthquakes. So we applied that to Kawajan. This is an example, for example, at Merapi volcano in Java. And you see the same sort of proxy, so the seismic velocity over time. And you see that it increases during the dry season and it decreases during the rainy season. And then again, it increases during the dry season, decreases during the rainy season. So in Indonesia, it's very useful, but we have to be super careful about the rainy season influence and the dry season, of course, because sometimes it increases and it decreases, and it has nothing to do with the magmatic activity or the volcanic activity. I'm going to check if I have time. Yes, I still have time. So this has been then applied to Japan, that's the situation of seismic velocity based on 1,000 stations located in Japan. And you see in pink, purple, that there is nothing. And this is before the Tohoku earthquake, the magnitude 9 earthquake that occurred in 2011 in Japan. And you see the situation after the earthquake. And you see that you have red colors. Those red colors are volcanoes, actually. They're compatible with the place of volcanoes. And this is very useful because they are more, the velocity is decreasing more when you have a very active hydrothermal system. which is also the case in Kawajan. You have a very active volcano hydrothermal system, and that's why also we wanted to compute the seismic velocity. Okay, so I'm going to finish for this part to focus on the 2011-2012 unrest. So now it's 10 years ago. We started with my colleagues to monitor the volcano, and we were discussing well, almost every 2 weeks with Parjan and Paeri, and there were some volcanotectonic earthquake, like the typical background activity. Then there started to be a bit more earthquake, but nothing concerning in October, November. And then suddenly in December, there was a large increase of volcanotectonic earthquake. So 40 per day. Paeri climbed on the volcano on the 17th of December. The lake was gray. He said that the smell was really bad. And then we were thinking that an eruption would start, and in the end, nothing. But we started recording some low frequency activity that we called monochromatic tremor. I'm not going to explain exactly what it is, but I'm going to show you one seismogram after. So the volcanotectonic activity decreased, but the monochromatic tremor appeared, and we had never seen that before. They were recorded in January, but also in March. And then there were a lot of bubbles that were recorded at the surface of the volcano. I'm just going to close the window here. It's a lot of sun for one. Sorry for the noise. That's much better. Now I see my screen. So there was monochromatic tremor, and there was a lot of bubble, as you can see here on the surface. There was a lot of heat because the lake was very hot, close to 45 degrees. That's what you can see in March here. So of course, this is concerning, but this is useful to better understand the volcano. So the last parameter I explained earlier is the dV over V, seismic velocity. And you see, well, there's nothing much going on before December. In December, there's nothing. And then in January, we have a seismic velocity increase and decrease. So it's going up and down all the time. So this was very useful because it tells us that most likely we had a lot of gas rising towards the surface, but not only gas, also hot water. So just to sum up everything once again, you have volcanotectonic activity first, a very shallow earthquake, less than 1 kilometer of depth, or between 1 and 2. Then monochromatic tremor that started, the volcanotectonic activity suddenly decreased. And at that time, we start having seismic velocity changes on the volcano. And then we say, okay, well, what's happened? Because before December, it would have been very tricky to know what was going on the volcano and to increase the alert level. The good thing when you do research is that you can go back in time and just examine the volcano seismograms. And we found a very large earthquake back in May 2011. And this allowed us with our colleagues from, well, it's mostly thanks to the colleagues from USGS, to better understand how the volcano was behaving back in May 2011. So we think that what happened, together with Wendy McCausland and John Pallister, that back in May 2011, there was an injection of deeper magma towards the surface. And this completely stressed the volcano. And first release the stress towards the external part of the volcano. It's what we call distal volcanotectonic earthquakes. At that time, there were not enough stations to make sure that or to locate those events, but they were outside Kawajan itself, so outside the main edifice. We also noticed that there was an increase of CO2 in the lake, and CO2 is a very interesting magmatic gas because it doesn't react with the hydrothermal system. So it goes all the way towards the surface and you can measure it in the lake. So there was an increase of CO2, but that's it. No change of water temperature, level, no change of in terms of volcanotectonic earthquake, so close to the volcano, no monochromatic tremor, not much in the system. So it took a bit of time, but after a few months, we think that the stress was finally released in the upper part of the system in terms of volcanotectonic earthquake. At that time, there was mostly brittle failure in the crust, and you don't have seismic velocity decrease or increase. You don't have much low frequency activity. So it's mostly a brittle problem. There is a bit of disturbance at the surface. The lake became gray. There was a bit of bubbles. But finally, after, oh, I forgot the last graph. Oh, I'm really sorry, but there was one more photo that shows you that the system has been opened. And when the system is open, you can have seismic velocity decrease and increase. You can have monochromatic tremor and low frequency activity. And you have fluids that are finally rising towards the crater lake. And in that case, you have increase of heat emission, increase of gas, you have lots of bubbles. And that's our conceptual model that we built with USGS and with our colleagues from CVJHM. Okay, one last thing I would like to stress. I still have 10 minutes, so that's going to be just right in time for the continuous monitoring. It's something we learned at Coagen is that we think before, well, let's go back to the history, everyone thought that acidic lakes are super homogeneous and that you have a big pool of acids that are completely mixed because you have a lot of convection, a lot of gas, a lot of fluid that will homogenize the lake. So basically they thought that the lake should be pretty much the same everywhere. If you sample the lake at the surface or at depths, you have the same temperature. In fact, by going back to the history, we realized that there is a shallow stratification that develops during the rainy season. So there is no mixing of the cold water. There's a lot of cold water due to rainy season with the water from the lake. And that is very important when you do monitoring. And that's what we realized by comparing the data from our colleagues from CVJHM that were sampling the upper part of the lake and my data as well with our data from the deepest part of the lake. So we were measuring 20 degrees centigrade at the surface, and at depths, it was more than 35. And this is quite easy to understand because when you have cold water, the density of the cold water is much lower than the density of Kawajan. Kawajan, when you take the lake water in your hands, it's a bit viscous. And we think that what happens is that the cold water can remain stagnant on the hot water. So I'm showing you here a few thermal infrared photo. I'm not going to enter the detail, but essentially, if you see the lower photo here, you see that you have cold water that doesn't mix directly with the hot water in red. So the cold water is in green, the crater rock is in purple, and the cold water just enters the lake, but doesn't mix with the hot water. It stays on top of the lake, which means that we have to be super careful when we do monitoring and that we should rather try to get data from the deepest part of the lake or at least a few meters below the lake surface. So it's something now that we have learned thanks to this project. And I'm just showing you here what I was telling before is you have the data at the lower part of the figure, the lower graph, you see the data on top of the lake during the dry season, no problem. And then boom, it drops 20, 25 degrees centigrade. And when you have the data at depths, at 3-4 meter depths, you see that they are much higher, the difference of 20 degrees. So it's very important because it shows us that Kawajan is not well mixed over time and that we have to be super careful with that because it's, of course, it biases the lake temperature and the monitoring efforts. And another example is when you have a landslide, you see that instead of directly, the rocks won't dissolve directly and within the lake, they will float on the lake surface and progress towards the center of the lake. Okay, I'm just checking the time. I still have a few minutes. The last thing we did is non-continuous monitoring in the caldera and in the Kawajan crater itself. That was better to better understand the structure of Kawajan, because as I told you, the propagation, when you have a seismogram, you have also the contribution of the propagation. And if you want to better locate earthquakes, you need to know what we call the velocity model. What is the traveling velocity within the subsurface? To do that, we did many measurements, more than 100 measurements in Kawajan crater, but also in the caldera, as you can see here. And this allowed us to better constrain the velocity model in different parts of the caldera. So in path 1 from Blawan to Paltuding, and path 2 from Blawan to Gunung Genteng. So I'm not going to enter detail because it's not relevant here, but that allowed us to better build or better understand the velocity structure. It's actually very slow when you are close to the surface, and of course, as always, increase when you are going to deeper portions of the crust. Okay, And the very last thing is that we did some echo sounding to compare the results in 2010 with the profiles that were acquired much before that during the 20th centuries by different scientists. And this allowed us to realize that the lake was actually much smaller in terms of volume. The deepest part of the lake was 165 meters. It's the green color you can see here. Whereas 100 years ago, it was nearly 200 meters deep, which means that the lake filled over time, probably with landslides, with precipitates, and the volume was 40 million cubic meter a century ago, and now it's 30 million cubic meter, more or less. And another thing that we learned, so that's me on the boat with Alain Bernard, well, a long time ago now, we deployed an echo sounder. What is an echo sounder? It's just a device, an instrument that sends acoustic wave in the water. And the cool thing is that when there is a target, like a bubble, the waves are going back to the transducer. And this can help you to know the bottom of the lake, to know the depths of the lake, but also where the bubbles are. So that's an example. That's a kind of, it's like an echography of the lake that you can do with pregnant women. You can do the same thing with Cawajan. You have the bottom of the lake here in red, and then you have huge plumes of bubbles and sulfur spherules, that are rising towards the surface. And as you most likely know, there's a lot of sulfur spherules that you can see floating on the lake itself. That's a photo where you have the sulfur spherules and you have the bubbles here that you can see very clearly close to the solfatara, close to the main fumarole. And this allowed us to build a map of degassing in Cawajan. And as you could expect, most of the gas is emitted at the center of the lake, but also close to the shores, as you can see here, close to the fumaroles. An example of a bubble rising towards the surface. And I'm going to leave it here. Take any question if you have. And thank you again for the opportunity to talk with you today. Thanks.
Okay, thanks, Corentin, for the very complete, clear, and very interesting explanation about the geological context from the Kawajan, present activity, and the future possible activity by the multi-monitoring system in the crater. Before we get the discussion session, maybe I would like to invite the General Manager from IJN Geopark, Mr. Abdillah, to get some remarks for this discussion. Okay, Mas Abdillah, can you get some remarks on the discussion?
Okay, thank you, Firman. Good night from Indonesia. Good morning, Corentin. I hope you are always fine. I always remember the couple of friends, volcanologists, Maurice and Katia Graf, that introduced Kawajan to the world wide for the first time in I thought you know them, and you also have a good memory studying IJN several years ago, and I'm sure you already miss it. My name is Abdillah from IJN Geopark Management. On this excellent opportunity, I would like to say thank you and welcome to the International Volcano Academy Forum. As an UNESCO inspiring global geopark, IJN Geopark must appear on the international scene as one of the learning centers in the world. We have 10 cultural sites, 6 biological sites, and of course 21 geological sites. Several of them is related with volcanism. The science of volcanology is important because it is closely related to society and the main theme of this geopark. We have a subduction system that produces 30 million years old volcanoes. We also have an active volcano that just erupted this year. We have calderas, cinder cones, submarine volcanoes, crater lakes, fumaroles, solfatara, hot spring, and many other volcanic phenomena. We have Kawajan, the most ancient crater lake on our planet. The crater is our main geological theme, but I am sure that behind it is majestic phenomena. Kawaijan have a lot of secret that we all doesn't know yet. So this discussion will greatly add to our explanation regarding this. However, on the other hand, interest related to volcanology still need to be increased, especially for young people. We hope that in the future there will be many volcanologists who take care of the volcanoes in Ijen Geopark. Therefore, we initiated a discussion forum with international volcanic research to gain wider experience and knowledge about volcanology. We hope that through this forum, we can establish cooperation and collaboration in the field of the research, education, and especially volcanic disaster mitigation in the future. We hope that the Ijen Geopark will become a center for volcanic studies, not only in Indonesia, but in the world. Thank you very much.
Warahmatullahi wabarakatuh.
Welcome to today's discussion.
Thank you.
Thanks, Mas Abdillah. Yeah, very good remarks from the Geopark.
Waduh.
So we move to the discussion session. There is some question in the chat. Maybe for the participant who have a question can use the raise hand or just text your question
Ya,
in the
terima kasih
chat.
Pak Irwan.
We can read it and ask it to the quarantine. It's okay, quarantine. We move to the discussion session. Okay. Maybe I go first to the chat. There is some questions. The first is from Mas Andi Volcano. There is two questions. Can you, Mas Andi, do you want to speak directly or I just read your question? Mas Andi?
Hello.
Okay. Okay, Mas Andi.
Can you hear me?
Yes. Please maybe ask directly to the committee.
Okay. Thank you very much for these happy occasions. Bonjour.
Bonjour.
Quarantine. Enchanté. Merci beaucoup. Thank you very much for this occasion. So I have very interesting here because your presentation was very, very cool for us.
Yeah,
so I'm volcanological tour guide, specialist in Indonesia. So I've been to many active volcanoes. So I have in Ijen, especially this is very, very most interesting for me. So last times, when Ijen was active couple years ago, so I found like a globule sulfur. So it's like juvenile fragments, very small, floating on the lake. So I was wondering what cause of this, So this is what cause of this. So why when Ijen is being active and then there are a lot of globule sulfur that floating on the surface. So this is the first question. And the second is when was active also in the 2012. So also that we saw this there was flame on the lake. So this is maybe what caused why there was flame on the lake. So maybe first two questions, Mr. Cordia. Thank you very much.
Thank you for your questions. So the spherules, they come from the bottom of the lake. So at the bottom of the lake, you have the liquid pools of sulfur, because the sulfur is a tricky parameter in the sense that is viscosity, and it can change of phase when you are depending on the temperature. And this is something you can actually see quite clearly when you are close to the salpatar, the fumaroles. It can be liquid, it can be solid. It really depends on the temperature, on the pressure, etc. What we think is that when the volcano is more active, it will produce more native sulfur. And of course, when it's more active, you have more bubbles, which means that they can be more easily rising towards the surface, because you need bubble to carry the sulfur spherules, the globules, towards the surface. Otherwise, they would stay at the bottom of the lake. So what we think is that there is more gas at the bottom of the lake. The volcano hydrothermal system is more active. You have more bubbles, so they can carry more spherules towards the upper part of the lake system, because it's quite deep, 170 meters. You need a lot of gas, and that's why we think that you see more sulfur globules or spherules at the surface. And it's actually a very good question, because it's something we thought about 5 years ago with a colleague from Italy. We say, oh, that could be cool to be able to monitor the volcano just by looking at the sulfur spherules, because you can do that with the CCTV installed by the CVJHM, which is super useful. It's probably one of the most important tools to monitor Kawajan. But you can also do that from space by just looking at the satellite image. And we think that we could count the sulfur globules to know when the volcano is more active or where when it's less active. So that's the first, I think, well, my first answer to that. And again, if it's not clear, just don't hesitate. I can re-explain or try to re-explain. And the second part, the flames, I didn't know that. I spent, I think, in total 6 months or 1 year in Kawajan during my PhD thesis, and spent a lot of time discussing with the sulfur miners and etc. It's actually them that told me that there was more gas during the rainy season. That's how we realized that maybe the lake was stratifying and that there were bubble explosion when it stratifies. But I never heard about the blue flames. So it's most likely, again, a problem due to gas. I should ask my geochemist colleagues, because I don't want to say anything stupid, but that's definitely due to gas. And if the thermodynamics of the temperature and the pressure condition changes, you can have more gas at the surface. There is actually, at some point, there was a multi-gas installed on the system in Kawajan, close to the dam and also close to the POS. I think Parjan could explain that better than me, because I wasn't at Kawajan at that time. But we did a test in 2014. It was very useful because during the phreatic eruptions, there is a lot of CO2 that, of course, goes towards the lake volume, reaches the surface, and then you can have intoxication, of course. So it might be due to one of those gas, probably not CO2, but maybe H2S or SO2. But yeah, it's very interesting to know. I didn't know that you could see those blue flames on the lake itself.
Yeah, thank you very much. This is really can increase my knowledge, because when I got clients, but after pandemic is over, because it's been 2 years, nothing. my client mostly geologists and volcanologists from Europe. Thank you very much.
Thank you.
Maybe I will have next after this.
Okay. There is a question in chat from Yuli Sofianti. If Mount Ijen erupted, what might mostly comes out from the crater? Please answer, Mr. Corentin. Sorry, still mute.
Sorry. Yeah, I just click on the not on the right place. Sorry about that. Yeah, it's again a good question. We have a big problem when we have lakes. It's not only just one thing before I forget, for the previous questions, something which is also very interesting if you see it and very important. Sometimes, and I've seen that only once close to Pos Baru, you have green sulfur, and this is sulfur that is due to explosion. So it's not yellow, it's green. And we see that, for example, in Dempo, also in Indonesia, in Sumatra. And so it's something you could also see in Kawajan. If some tourists ask you what it is, it's sulfur that is expelled during a phreatic eruptions. Getting back to the other question. So the problem when you have a lake is that you have even more hazards. And So that increases the risk, of course, if you have people around the volcano. And that challenges our job as people like me or people like Paparjan or everyone who is doing monitoring has a problem or has extra problem when there is water, because you have classical eruption, it's lava. So you have to be careful with lava. There are pyroclastic flows like a Merapi volcano in close to Yogyakarta. You can have those pyroclastic flow, you can have lava, strombolian explosion, etc. That has been occurring in the past history of Kawajan. We know that. This has been documented through the history. When you have phreatic eruption, you have another problem. And when you have magmatic eruption, well, let's get back to magmatic eruption. You could expect also when, due to the interaction between lava and water, you have explosion of water vapor at the surface. But the problem in Kawajan, when you look at the crater and the Banu Pahit, you can have lahars because you have a lot of water. And extra problem, Kawajan lake is acidic, which means that it's even worse because it's acidic water. So you better, if there is an eruption, you better stay away from the river's bed, because the lahars will just follow the topography, the elevation in the caldera. So that's one extra problem. It's the lahars. And then in Kawajan, you have another problem, is the phreatic eruptions, explosion of gas, which means that if you are a tourist or if you are guiding tourists or if you are working in the crater, if there is a phreatic eruption, there is a danger of gas expulsion and intoxication. Phreatic eruption can emit ash up to 10 kilometers of height, of altitude. So it's quite high. It's a big eruption, although there is no lava. And then the last thing you have to pay attention to is those eruption that we call limnic eruption. And the limnic eruption, it's an eruption without any volcanic input. So it's not a phreatic eruption because there is no change in the volcanic activity. It's not a magmatic eruption because there is no magma at the surface. The problem is that it can be due just to the lake itself. And that can happen, for example, we think that it can happen during the rainy season when you have this cold water layer that forms and that develops over time above the hot water. And we think that the gas can be trapped in this hot water layer, which is the major part of the lake. It will be trapped. It won't reach the surface. It will accumulate. And at some point, just because of an earthquake or just because of rain, it can destabilize the full lake structure, and you can have an emanation or an emission of gas. Gas are toxic. CO2 is toxic. You better not be there if this happens. So that's an extra problem when it comes to eruption. And it's not a volcanic eruption. It's a limnic eruption. It's just a lake eruption, but that happens. It happens at Kawajan. It happens at other lakes. In Cameroon, in Africa, it killed more than 2,000 people because the CO2 is more dense than the gas in the atmosphere, and it will flows again like a lahar and follow the topography. So that's another problem in the case of Kawajan. So I think I kind of talked about the different hazards and the problem we can have with eruption at Kawajan.
Okay, thanks for the answer, Corentin. I hope the answer is clear. Yes. I think also that the Kawajan have a specific product from its eruption. It needs a specific monitoring too or mitigation system too. We move to the next question from Mas Lamat, Jenjopak. Is it the color of the lake can show that the gas increase, and how close the visitor or tourist can see the lake when the color of the lake changes or getting white? Maybe this is related with the tourism. Corentin.
Yeah, well, again, a very good question. We've discussed that many times. There is no clear answer. I think that most of the time, you kind of save. Well, no, the first response or the first answer is that you're never safe when you are close to the shore, a few meters away from the lake. It's a huge lake, very acidic. There's a lot of gas, so you can have an eruption at any time, even if the lake is green. As I said, those limnic eruption, they are triggered by nothing. They can occur just like that at some point, big explosion, most often during the rainy season. The good thing to know. If the lake is getting white or gray, I would be super careful and not go down, just stay on the rim, because it tells you that the lake temperature is increasing, so there is more fluid coming towards the surface. But one thing which is very important that we have discovered with our colleagues from CVGHM and from USGS is that unfortunately, phreatic eruption can be triggered by top-down processes. What I mean by top-down is that at some point, at the bottom of the lake, you have a lot of sulfur, you have a lot of silica. Those things can seal, and they will, again, not allow the gas to rise as they should go towards the atmosphere. So we stay below this seal, and at some point, for any reason, you have a big explosion. And the lake can be completely green. That's what we saw in March. The lake was green, temperature normal, 35 degrees centigrade. And then out of nowhere, boom, big explosion. And the sulfur miners evacuated at that time. The tourists were not climbing. So well, as I told you, I would never go anymore on the lake itself myself with the boat. That's something I will never do anymore, not again. But I will also as far as I can, stay away from the lake shores, so a few meters away from the lake, and on the rim if possible. And the view is usually better when you are on the rim anyway. It's fun to go downstairs and to see the lake, but it's a nasty lake. It's super acidic. It's very dangerous. And if you see white color, just be careful.
Okay, thanks for the answer, Quentin. Yes, maybe the activity of the lake also have direct related with the tourism, because
Yep.
yes, we have now we have geopark, attract tourists, more tourists come to the crater, and the well monitor is being needed to discover again. Okay, we move to the next question. Okay, from Mbak Tantri. Okay, this question maybe about not directly related with the volcanology maybe, but this is related with culture. Is there the 1817 eruption of Kava Ijen produced pyroclastic flow? Because in 1840, it's about 20 years later, the early people that inhabit the Ijen caldera creates a single olung dance, the lion with white fur all over its body. That's I think it's related with the pyroclastic flow phenomena. Is it possible or not? Thanks.
Yes, yeah. So definitely there were pyroclastic flows. I'm not an expert in pyroclastic flows. As you understood, I'm more into the monitoring. And yeah, we just would like to point the fact that the monitoring system in Kawajan is already excellent. So that it's difficult to do better than that. And even if I was there just to work every day, I would struggle to do a better job than what they are doing. In terms of pyroclastic flows, yes, there were pyroclastic flow in 1817. The worrying thing is that there were pyroclastic flows directed towards Banyuwangi, I think. That's something we suspect based on the old books I mentioned earlier. Something Vincent van Insberg could definitely better comment on than myself. But yes, it's possible.
Okay, very interesting. Yes, in Banyuwangi, in the south eastern part of the Kawajan, also known the legend of Macan Putih. You know, the white tiger, maybe also related with the pyroclastic flow phenomena erupted in 1817. Yes, there are a lot connectivity between the geology, volcanology, and another aspect in Kawajan. Okay, thanks for the answer, Quentin. We move. Yes, there is also a question from Mas Lamat again. Mr. Corentin, we need your advice as geologists. How close? Maybe related with the first question, we can see the bullfire. The bullfire, as we know, the many tourists come to Ijen, want to see and take picture uh, for the bullfire phenomena, especially for bullfire phenomena in the Salvatera area, be related with the gas explosion or like the. Yes, that's the question, Corentin.
Yep. Yeah. Well, I've been discussing that with colleagues who are as old as Morris and Katja Kraft if they would be alive, and they say that back 20, 30 years ago, the blue fires were less big than they are now. Vincent van Insberg and others also said that, people who have been on the volcano for decades. So it's something which is more active now. I don't know if it's because there's more water that's being poured on the system to generate blue fires. That's, I don't know. But again, I would stay away, tens of meters away from them. I was only once trapped. I needed to take a sample of the fumarole. So it's a very specific thing. You need to really go with the mask, with a gas mask, a very good one, within the fumarole. You have to be super careful. I had everything, and I was trapped in the fumarole, and I really thought I was dying. So it's awful. You have to stay away from this as much as you can. I know the tourists will try to get as close as they can, but please tell them to stay a few meters away as much as possible. It's nasty. It's 400 degrees Celsius,
Yeah.
sometimes even more. So yeah, I wouldn't want to be burned by those things.
Yes, I agree with you. Yes, today we maximize the equipment for the tourists for they are going to down to see the crater and the bullfire. They must using the mask, and yeah, we now maximize this equipment as better as possible.
That's excellent.
Yeah. We move the next question. This from the Sirun volcano file. Okay, Salut Corentin. Can you show me the acidity of pH level of Ijen water lake? Is the acidity of rainwater can influence the pH of the lake? Maybe is the rainwater can change the pH level?
Yep. Let me find the slides with the water color, the pH. Maybe I have it here. Maybe not. Damn it. No, I don't have the pH here. So in the very valuable data we've collected from CVJHM library and compiled, the acidity is always more or less between 1 and minus something, minus 0.5, minus 1. So this is super acidic. It's not the only lake in the world that is that acidic. So there's a few lakes that are more acidic than that, like Poas in Costa Rica is sometimes more acidic, but it's much smaller. So Cahuajan is the largest for sure in the world. So I could try to find the graph of the acidity, but I can find it if needed later, and I can answer Daziron later. Now, the acidity of the rainwater, if it can influence the pH of the lake. So the water is always pretty much the same pH. It's rainwater, it's around 7, let's say. So that's always stable. It will influence the pH of the lake if, for example, there is more rain that falls and that flows on the slopes of the volcano and that enters the lake. It will definitely influence the pH of the lake. Now the lake is too big to suddenly rise by a few units of pH, so that will not happen. The photo I've showed you with the brown colors is, for example, a huge rain that triggered some landslides. The water fell into the lake. There were some precipitates, brown precipitates that formed. But at some point, the lake is too acidic, so it will just go back to the previous acidity. So the rain itself will just influence the few meters that are just stagnant during the water, the rainy season on the lake surface, and that's it. And then it will get mixed during the dry season.
Okay, thanks for the answer, Quentin. Yes,
No
the
problem.
pH level is also some interesting phenomena that our geopark also using the maybe the extreme pH level from the lake as the main geological time, because yes, we know Kawah Ijen may be the largest acidic crater lake on Earth, maybe from the research that this is something we must conserve maybe in the geopark goals. Okay. Okay. Next, we move to the next question from Mr. Johan Pramono about the hazardous limnic eruption that you studied based on past data and maybe models from other similar mountains. What is the safe radius you should suggest for the this eruption? Thank you for thank you and a very great presentation. Okay, thanks.
Thank you. Wow. We don't know, so I don't have any answer myself. I'm sorry. It's something we wanted to do with, well, Padevi, Shabana, and others, is to do modeling and to see how what would be the extension in terms of CO2 emission from a limnic eruption. It's something we have to do. We know the structure of the lake very well thanks to the bathymetry. We know the DEM. We have the digital elevation model of the crater itself. So it's something possible that we can do, but we don't have any models. And unfortunately, I don't have any answer now. It would be very useful, but definitely if, for example, if you visit Kawah Ijen in March, April, May, even June maybe, or May, I wouldn't go down towards the crater, because those limnic eruptions are more likely to occur during these days, during these months and weeks, when the rainy season has been there for a while already, and this cold water has accumulated a lot. But I would need to do some modeling, and I'm going to take an example from Congo. There was a big, well, not a big eruption, but there was an eruption this year, and the eruption was close to Lake Kivu. And Lake Kivu is a huge lake, much bigger than Kawah Ijen. It's neutral. There's a lot of CO2 dissolved, so a lot of gas, like Kawah Ijen, dissolved in the lake. There's 7 million people who live close to the lake, and we don't know what would be the impact of such a limnic eruption on the people. Should they stay away from a few meters from the shores, further away? No clue. I don't have any answer, but it's definitely something we need to do in terms of research. And I think it would be quite not easy to do, but it's quite possible to do modeling and to better know what are the security perimeter that we have to consider.
Okay, thanks for the answers. Very interesting. Talking about the limnic eruption, something new maybe for us to understand that. And maybe yes, I agree with you that the research can answer more specifically about these specific eruptions. Okay, maybe there is no more question in the chat, but this is maybe also yes, Mas Suparjan from Indian Volcano Observatory. Maybe there is some question for Quentin. Maybe your old friend. You have a very good collaboration in the past.
Yeah, we are often in contact.
Then maybe Mas Suparjan, this question for Quentin, or maybe will speech for us. Okay, maybe yes, it doesn't chat. Merci for Pak Koko. Yes. Okay, maybe we move. Yes, Mas Andi raise hand. Maybe another question for Mas Andi. Okay, time's yours.
Okay, I'm sorry because I'm very exciting, yeah, Mr. Koko.
That's good.
Yeah. So like this is not question, but it's like more discussions, because I love volcanoes and the phenomenon of eruptions. But in this case, I would like to ask about lately, since pandemic, I don't know, maybe before. So the volume and the pressure of the solfatara gas into sulfur mine, so it's like lower, lower and then less. And then this is also make the blue flame is also lower. So I went there like 6 months ago until to the blue flame, but was nothing. So I don't know, because this is the miners, they pour water to kill the blue flame, or this is because the solfatara gas, the heat of the sulfur gas is lower. So maybe this is there any relations that you can observe this in the monitoring systems, that also in the seismic that is lower? I mean, like the tremors or whatever. And the second is like this. So like opinion from many people. So why the blue flame in the crater now is less and then lower? This is maybe related with the maybe, do you know geothermal? So there is like new geothermal power plant in the Kawah Burung. So it's like also in the same complex. So maybe this is caused by the geothermal, and this is make the change, of the blue flame and then become lower. So if there's any relation or correlation between geothermal plant that they dig all the gases, or the thermal, and then this is influence the blue flame and then become lower. So there is like two discussion. Thank you very much.
Thank you. It's again a super interesting comment. And well, as I said, some of our ideas in terms of research came just by discussing with people who are visiting the volcano more than me or others at that time. So it's very useful observations. So based on what I know from people who were working with Maurice and Katja Kraft and all these very old guys, there has been some fluctuation over time. If you compare the activity in the 90s, 80s versus now, well, at least no, 2010, they say that before that, they could go without any gas mask within the crater, close to the fumaroles, the solfatara, they could even work on the lake without any mask, no problem. This person is smoking a lot, no problem. And when we went back together in 2009 and 10, he told me it's really dangerous. We have to have masks. If at some point the wind changes, it becomes really intoxicating for us. So he told me that there was a big difference, and the volcano seemed more active. So maybe now it's doing a new cycle. The volcano, based on what we know, the volcano has evolved in terms of cycles. So there are a few years when it's completely quiet. As far as I understood, in 2011, there was a new cycle that triggered some phreatic eruptions for a few years. Maybe we enter now a new cycle when everything will be more quiet, and that would be good news, of course. To answer the part of how we can monitor that, you exactly talked about the right thing, tremor. That's something quite interesting. It's more anecdotal, but the first people who installed the seismometer in Kawajan in 1980 something, it was people from USGS, and they had the same sensor as the one they installed in Kelut volcano that you probably know very well too. So they took the same sensor, the same specification, same gain, blah, blah, blah. So they just install it on Kawajan and say, whoa, the seismogram is completely saturated. We can't see anything, which means that the volcano is making too much noise, which now we call tremor. And they had to decrease the gain so that they could see something because it was way too high. And the good thing for research, it means that there is always an excitation of waves in the volcano, and that we can track that over time. And this is tremor. We can also use it as a way to know what's going on really at the shallow level of the volcano. And this is one way to do that. Back in 2014, we installed an infrasound, and you have an infrasound most likely in your pocket. Any iPhone, any Samsung has an infrasound detector, and you can use it there is an app, it's called Redvox, that can help you to record the level of infrasound. So it's acoustic wave that the human can't hear, so it's below 20 hertz. The elephants, some animals can really well see that. In Kawajan, there is infrasound all the time because of the fumarole. And we noticed that by doing a 3D deployment close to the dam, and we could still detect the infrasound at the dam. So you could do that with the iPhone, you could do that with a Samsung, that works. And so that would be one way to track the fumarolic activity just with acoustic waves below human hearing, so below 20 hertz. So there are different ways to monitor the tremor, and it's definitely the way to go. It's to check this tremor over time, and we do that. Well, we've been doing that with Pasuparjan and others. It's very efficient. Now, the question regarding geothermal activity, you're right, that could be something. That's very interesting. Usually we think that Kawajan plumbing system is really below the volcano itself, but there are people suspect some connection between, for example, Raung and Kawajan. There are some suspicion that they could share the same reservoir quite deep in the crust. And of course, any activity in terms of geothermal activity can also impact Kawajan system. So that could be an explanation. I should check exactly where the geothermal activity and the power plant is, but yeah, that's possible. So thanks again for it's very interesting remarks and questions.
Yeah, thank you very much. So I think now I get it already, and some that I can explain to my group next times. So do you think fluctuation of the blue flame is also because of the fluctuation of the gas pressure or gas supply like that?
Yeah.
All right.
Yeah. What we think is that you have a main. So there are two main zones where you have gas. You have a conduit that feeds the solfatara, the fumarole directly. And we think that this is completely decoupled from a main volcano hydrothermal reservoir beneath the lake. And so we have two exits for the gas, and those ones could be actually decoupled. We don't know exactly. We need what we wanted to do at some point, and we did that, but I have only 12 hours of recordings. We put a microphone in the lake to listen to the bubbles in continuous. It worked very well, but we lost the hydrophone because at some point the sensor disappeared. And that would be one thing, is to monitor the acoustic in the water close to in the lake, and one close to the fumarole, because these are two exits, and everything depends on the pressure on the system.
Yeah, thank you very much, Mr.
Thank you.
Yeah. So I live near Merapi. Yeah. So if you come to Jakarta, so yeah, please come.
I was supposed to go
every day. Yeah.
I was supposed to go to live in Merapi for 2 years, but pandemic complicated.
Yeah. I live very close here. Every night almost. Yeah. Thank you very much. Maybe
Pleasure.
Other participants.
Okay, thanks, Mas Andi, for the question and answer from the quarantine. Yes, yes, I have just checked the chat. There is one skipped question from Mas Abdullah. Okay, Mas Abdullah, the question: why in the Caldera volcanic complex, Ijen volcanic complex, so many volcanoes, only Ijen that have a crater lake with the extreme acidity? Is there any specific magmatic system beneath it? Maybe related with the name itself, Ijen in Javanese have meaning the only one. Maybe related to that.
Yeah, thank you. That's again a good question. Well, I don't know if you have seen the photo from volcano in the Philippines, Taal. There was a big eruption. The lake was much larger than Kawajan, much bigger volume, and it was all emptied by the magmatic eruption. Very early, and after a few months, there was already lots of water accumulating in the crater lake. We know that after the phreatomagmatic eruption of 1817, very quickly there was again water in the crater, and this was a big eruption, so that completely changed the morphology of the lake. So you just need a big depression, and you need some rainwater that we call meteoric water in scientific jargon, that comes to fill the depression. And for Kawajan, you have Merapi, not the Merapi from Jogja, but the Merapi from Ijen caldera, that where water flows, and most of the rainwater comes from the flank of Merapi, infiltrates into the Kawajan crater, and feeds the lake itself. So you need two things: a big depression, like a small crater, and a lot of water to fill that depression, and then it works. I think there is another lake that forms during the rainy season on top of Merapi. I've seen that on satellite imagery, and this has been confirmed from photos, but it's much smaller. So yeah, you just need a special morphology and a lot of water feeding this depression.
Okay, thanks for the answer, Quentin. As we move to the next question from Mas Cristianto. For the type of Ijen crater, what type of volcanic quake must be considered as a precursor before a phreatic or major magmatic eruption? Thanks.
Thank you. Again, very good question, Pak Cristianto. The complicated one, because we don't know exactly yet. So far, in case what I would do and what we've been doing over the years, I'm less actively involved in monitoring Kawajan currently, but what we were doing with Pasuparjan and others, for magmatic eruption, I think and I hope that before a new type of activity, we will have a lot of deep or distal volcanotectonic earthquakes. So earthquake not directly beneath the volcano, but move on faults located close to the edifice. And that would be great because it would tell us that we have a few months before anything happens at the surface. So that's really the hope before magmatic, a new renewed activity, a new magmatic crisis. I really hope that's how it will develop. Definitely VT. I hope we will see volcanotectonic earthquake before that. Before phreatic eruptions, in terms of earthquakes, if we focus really on earthquakes, I'm afraid there is no precursor, or it's just a few minutes before we may have a VLP. That's what we have seen on different volcanoes. In Kawajan, it's at the time of the eruption, but the problem is that we didn't have the timing of the 2013 eruption because everyone gets scared, of course, and escaped from the crater. So we don't know if the VLP and the 3 VLPs we have seen occurred before the eruption or during the eruption. And that's where the information from tourist guides is very useful, from the people who are working and visiting the volcano are super useful. This being said, we have found that Kawajan and other volcanoes that we have a change of a parameter that is using continuous seismic noise. A study we've done with Pak Cristianto and others, by the way, at Kawajan, which is called DSAR. And we use the tremor of Kawajan to know what's going on just beneath the lake. And we saw a big change, a big increase of this DSAR parameter prior to 3 phreatic eruptions at Kawajan, a few phreatic eruptions in New Zealand. And I think that's the most promising with seismic velocity. So that I would go for that, and we can install the software. They're already running at different volcano observatories. So that's what I would do if I was monitoring the volcano on a daily basis.
Okay, thanks for the answer, Quentin. This might be yes, I check the time. Be just very limited time for us. Maybe I want to give you the last question from me, Quentin. Yes, I live in the western part of Raung Volcano. Raung Volcano is just about 30 kilometers from Kawajan. Yes, I study this volcano in my undergraduate study. I studied the petrogenetic characteristic of the Raung Volcano. Yes, I agree with you that in petrogenetic aspect, the magma beneath the Raung Volcano has a similar characteristic with the maybe Kawajan and older Ijen, the Ijen caldera system, especially its basaltic andesite hycalcalin system. I agree with you, but in the deeper level, in the crust level beneath the volcanic complex, these two volcanoes has a sharing magma system, but has a different superficial system. We can have a crater lake with water, and Raung, there is no lake there. Yes, maybe my question is, what is the main monitoring system that we can approach with these two volcano with the maybe not so far away distance, and maybe is there any possibility if Raung active, Ijen also active, or vice versa, the Ijen active, Raung can active? Maybe this is the main question from local people. If Raung active, can the Kawa Ijen also active, or the like vice versa?
Yeah,
Okay.
thanks.
My question, Quarantine. Thanks.
Thank you. Well, it's again a very good question. Very difficult to answer, to be honest, and one of the most difficult. I think the monitoring system already in place now is already of very high standard. Well, I mean, I'm not the first one to say that, but our Indonesian colleagues from CVGHM, they're among the best one in the world. It's a huge amount of volcanoes that are active at the same time. There is a seismometer, at least one seismometer installed on all volcanoes, sometimes broadband. So it would be difficult to do a better job in terms of monitoring than that. This being said, that's monitoring. Then we do research, and that's my job. I do research, and I hopefully contribute to the understanding of the volcanic systems. So what is needed, I think, is to do a big tomography experiment to know. It's getting back to the slide I showed in the beginning. When you have many stations, you can know the image of your plumbing system. And at some volcanoes, you have a detailed image of the system. So you know if there is a connection between the volcanoes, if they have the same reservoir that feed them. And that's one thing. And to do that, you need many stations, more than 50. So it's a huge job. You need many people to help you. We tried to do that back in 2010-11. We managed to install 12 stations, but it was tricky. In some places, it took a day just to install one single instrument. So it's not easy, but that would be one thing. And that would be not it's not the monitoring, if you will. It would be more a research project to better understand the structure of Ijen caldera, and if there is any connection between Raung and Ijen. There might be one. Raung, fortunately, is doing some big explosion, but not massive one. There is no Plinian eruption. There is no dome like at Merapi. So the good news is that there is no water in the crater most of the time, so you don't have phreatic eruptions. So it's a dangerous volcano, of course, but not too dangerous, not too active those days, or not too big explosions, I would say. There is a possibility that when Raung is active, Ijen becomes active. That needs to be studied during statistical analysis and studying the activity of Kawa Ijen and Raung at the same time, the records we have, knowing if, for example, when Raung becomes active, the lake temperature of Ijen increases. That would be one thing. If there are more earthquakes, that takes time. It's again research. But in terms of monitoring, well, yeah, I've been doing continuous monitoring Kawa Ijen, and it's very challenging. So I think my colleagues are already doing an amazing job, and I don't know if I could do better than what they're doing already. So it's more doing a bit of research, a small project like a tomography experiment, and possibly installing more fancy instruments. But I showed you the example of lake level. Lake level in Kawa Ijen, I managed to have 6 months of data, but after that, the instrument was destroyed. So it's not easy. So yeah, I'm sorry, it's a long answer for not much of an answer, but I hope it provides some insight.
Okay, thank you, Corentin. Yes, I agree with you. It's challenging for us. Yes, if we want to understand volcano, we want to monitor. Yes, we must sacrifice maybe our time, our our effort to get to finish this challenge, to get the better monitoring of the volcano. Yes, thank you, Corentin, for the very clear, very complete, very interesting explanation and discussion. this very useful for us. You talk about the past geological context of the Kawah Ijen, the present activity of the Kawah Ijen, and future by monitor this volcanic activity in Kawah Ijen is very interesting for us and give us a better interpretation of this volcano Kawah Ijen. Okay, maybe before we close this forum, maybe there is a closing remarks from Pak Abdillah. Pak Abdillah, you still
Okay.
here? Okay,
Yeah,
maybe
okay.
there is closing remarks and maybe there is a video from Ijen Jopak. Okay, thanks is yours, Pak Abdillah.
Okay, thanks, Firman. Thanks for the interesting talk, Corentin. It give us a better understanding about Kawah Ijen phenomena, especially about the monitoring system of this activity. We realize that we need a better systematic mitigation there. I hope this forum is useful for all of us, can add knowledge and apply it in the daily life. I hope this forum will not be the last, but we can continue in collaboration and other collaboration. Ijen Geopark is very open to collaborate with all research in the world so that we can continuously understand the phenomena that exist in Ijen. Maybe in the future, there will be many things that can be done between the Ijen Geopark and your institution, both research, education, and disaster mitigation. I really look forward to this happening in the future. I will prepare you ahead, namely udeng. I will wait you from visiting us as soon as possible.
I hope very soon. Thank you.
Okay, thank you, thank you.
Okay, thanks, Pak Abdillah. Yes, maybe there is we can close this forum by using the video highlighting the Ijen Geopark.
People have eyes, but most of them are not really have. Only if they truly open theirs, everything will be different. Saying good night and good day for tomorrow. After and after. Then what? They fly away with the crowd. Wind and rolling wave gathered into one. Come to meet the reef that though the solid rocks, they're important, and the grain of sand that make these all complete. Sure me, they all are breathing, and that is life. What should I deny? And what about me as a human being? Time after time, nature always has its dignity. Dynamic, powerful, yet delicate. It collides, then form into countless repetition. I realize the process does exist. Between awake and asleep, from one secret to another, and also hope along the journey. So, this is what nature shows me. A gift. Where lesson, beauty, and future belong to.
Okay, thanks for the video. Okay, maybe before we close the Zoom, we can take a photo for our forum today. Can the participant open the camera? You can take some photo for our documentation. It's okay for all the participants to open the camera. Okay, and the other. Okay, maybe I want to take the first photo. Okay, 1, 2, and 3. Okay, okay, okay. Maybe the second photo. Okay. 1, 2, and 3. Okay, thanks all for attending our forum. Thanks, Konstantin, for having a discussion with us. See you in the another occasion. Okay, thanks, everyone. Good night.